All right. Okay, great. Okay, good. Then we can start with today's course. So, as always, we start with the questions from last time that has not been answered yet. So let me go to the first one. So, is the data sent and received, does it look like a single dimension array or like a multi-dimensional array? So is it like a camera sensor, CCD or CMOS? And also, I put these two together. The geometry was not yet so well understood. So what is range and what is azimuth? So I'm gonna explain that up again. But let me first say something. The first question. Well, ideally, okay, it would be the best, I think, if you try to avoid make such comparisons because they're not leading you anywhere. Okay, it is a very different system than a camera system. So any form of comparison at the end is going to be misleading you. Okay. Now, nevertheless, if it helps to understand, I will try also to humor you a bit in that. Let me show you the next slide. Okay, so first, let's do the basic directions. Okay, sorry. So in range, what is the range direction? Range, that means what is distance, right? So the range direction is the direction that your signal is traveling there and back. So range direction would be, if here's your sensor, right, it's the direction here that your signal is traveling. That is the direction where we measure the range, where we measure distances. This direction is also what we have here. So that this direction here is also called the slant range direction because it's slant. It's not straight, it's slant with respect to the ground. So this is the range direction, which is the direction in which the radar signal is traveling. And the other direction is the azimuth direction. That would be the direction that your sensor is moving. So if you think about this slide here, that would be the direction basically inside your screen, right? Or outside, or going out of your screen. So that would be the azimuth direction. That is the direction in which the sensor is moving. So next slide. So the azimuth direction you see here, that is the direction your sensor is moving in. So it is going in this direction, right? And range direction is then the direction which the signal is traveling, if you want. So one is these are the two directions, right? Sensor moving direction and your signal is traveling. Okay, now, because we had the question of can we
recording in progress?
Can we compare that to camera sensors or anything like that? Well, I would try to avoid any of these comparisons. However, because we have to understand that like, how can we say? Okay, so we have to understand that we have a rather large radar beam, right? So we are basically, when we are looking at the way the radar, the real antenna is acquiring the data, it acquires a lot of data, basically the whole frame, if you want, so in one time. So that would be rather comparable to a frame sensor, right? So one beam, one pulse, you could, if you really want to compare it to a frame sensor. But that's not what we are looking at in the synthetic antenna. In the synthetic antenna, we are using the satellite or the sensor, right? And while the satellite or the airplane or wherever your sensor is on is traveling in that direction, we take we acquire many images, if you want. Okay, we send out many pulses and we receive many pulses back. While each pulse is covering a large area, right, the resolution of that would be very bad. And what we're doing is, in synthetic antenna, we are taking all of these pulses together, right? We form then a larger antenna synthetically, and then we increase in that way the resolution. Now, coming back to your question, to which camera sensor we can compare that. Now, in that sense, when you look at your final image, your synthetic aperture radar image, each line in the image, okay, but each line we separate here these two axes. One axis would be the azimuth and the other would be the range. And we could understand each range line as taking more like a line sensor, because we're moving along azimuth, right? And then we are taking this data along the range lines. Okay. So that would be more like line sensor. However, that understanding of that would be very simplistic. Okay, because it's not the reality is that you cover with a large footprint in each images that you typically see one target, have data of one target probably in 10,000, 20,000 samples, 20,000, if you want, small images that you combine together to achieve then the focusing in range and azimuth. So I would strongly advise you to not make that comparison, okay, and to try to understand that you have here a very different system that acquires data rather differently, and a key point that we have is that one signal, one pulse, one of these radar lobes, they are covering a really large area. We had that, I tried to explain that when we discussed on that we cannot have a sensor that's looking downward because we are having such a large radar lobe, and then we couldn't separate each side. So you have to understand that at the very end, you have a very different system that you can compare if you want to a camera, right? If you really, really want it. But in most cases, my experience is it leads you to a misunderstanding, okay? It leads you to a misunderstanding that at the end, you collect not an image. It's not a picture. It is a very different kind of data. And so I would advise you to not try to think in terms of camera at all. Okay. Right. Now, another question is on the perpendicular and temporal baselines. What are good values for those? So just to repeat that from last time, what is the perpendicular baseline? So when we talk about SAR interferometry, we are forming, we need two images, okay, to form an interferogram. These images are taking from typically a slightly different position, and the distance between those is the baseline. The perpendicular baseline would be this one here. Sorry, this line here, right, it's the green one, the perpendicular baseline. We use that one mostly instead of the interferometer baseline. We use the perpendicular baseline because it allows us to form these perpendicular triangles so that we can calculate things easier based on trigonometry. right? So we use the perpendicular baseline, and then we have the temporal baseline, which means the time difference between these two images. What is the time difference? So we have a perpendicular baseline, the spatial difference, the difference in space, and the temporal baseline, which is the temporal difference. And the question was, which one is standard value, which one is the best? And it is very clear, right, that there is no such a simple answer to the question. However, I found a slide on that from Professor Oka to discuss a bit about it, about best baselines. Now, the baseline that we use, perpendicular and temporal, they have a strong effect on our quality. We have different decorrelation effects, we will come to that, right? So if you have a very long temporal baseline, if you have a very long time difference between the images, many things change on the ground. So often we prefer a smaller time difference. And in terms of the perpendicular baseline, the topography, as he wrote here, is amplified by the baseline. So if you have a very large baseline, you get a larger effect of the topography on the face, which helps you to get a higher accuracy at the end, precision actually at the end, but makes it, for example, more difficult to unwrap on that. And we come to that, right? We already got some questions on unwrapping, but we will come to that, right? So there is not such a good answer to that. Now, if you are, for example, it also very much depends on the application that you're after. Right? If you want to create a DEM, right? If you're interested in the topography, the temporal baseline, the time difference between the images should be very, very small as possible. If you're interested in motion, on the other hand, well, you need a time difference that is long enough that you can measure the kind of motion you want to measure. And if you have, let's say you have a time difference of 0, you take both images at the same time, there's not going to be any motion you could measure. Now, in terms of the perpendicular baseline, as written, if it's too large, you maybe have problems with unwrapping. If the images are very, very close together, if there's almost no baseline difference, you have almost no influence from the topography, so it's going to be hard to make a meaningful DEM out of that. So somewhere in the middle, right? Or, as you suggested, and we also come to that, I have some slides on that, a combination of different baselines, right? Combining different baselines, smaller and shorter, to overcome some of these problems. So there is no perfect answer for that. But still, to summarize, because it's a very good question, okay, still to summarize, if you're interested in the motion, you probably want a very short, small perpendicular baseline, because the perpendicular baseline, the distance between them, will, as it's written here, amplify the topography. And if you're not interested in the topography, you do not want that to be amplified. On the other hand, if you are interested in DEM making, you want a larger baseline and a very short temporal baseline. So, and ideally, maybe even multiple baselines, so you can solve the unwrapping problem better. All right. Important is, because you also asked for kind of rule of thumb, okay, we need to be far away from the critical baseline, and the baseline that are, you know, good or common baselines, they also depend on the wavelengths of your system. Okay, so the larger wavelengths, the longer baselines you can accept. And now, if you have something like an an X-band system, typically baselines are in the ballpark. 200 meters, 300 meters are totally fine. Even if you have multiple baselines, you can even go higher. And if you, for example, are using Sentinel, you wouldn't even need to worry about the baseline, because Sentinel is controlling the baseline very strictly, and there are no very large baseline images in the case of Sentinel. If you're interested in DM generation, typically your baselines are even too small, perpendicular baselines for you. All right, so not a perfect answer, but there is also is no perfect answer on that one. Okay. Now in terms of, maybe you can mute your microphone. Sishan, can you mute him?
Yes, Professor, I'm trying, but for some reason it didn't take me. Wait, please.
All right.
Yeah,
okay, problem. So for now.
If I was
Okay.
for some reason.
Okay. On the other hand, what I also wanted to say to you, so the baseline, for example, the perpendicular baseline, is not like you can as such order that. Okay, so you cannot, let's say you go and I say I want an image, a newly acquired image with a baseline of 200 meters or something. That's not how it's working. Okay, the satellites, they go around, and they are held within a certain cube where they can be inside, so to not have the baseline be too large. But at the end, at what position exactly they pass again, there is a certain randomness to that. So you cannot really go and say, I want 200 meter baseline for that. Right? One could, from archive images, one could look up and say, I want this baseline is too long. Right? I don't want that, but for newly acquired images, you can't really exactly or precisely control that. The agencies who control the satellite, they have more powerful that they can let the corridor of the baselines be more large or more short. They can control that. It is at the end a question of how much energy, how much basically gasoline, like how much of the fuel actually you want to spend on that, because controlling the baseline at the end costs you the fuel of the satellite. It reduces the lifetime of the satellite because you're going to have to control that again. So you cannot exactly choose those, right? You can keep them within a certain limit. Okay, I talked too much about baselines, so let's go on a bit. Okay, please explain how, and it's a good question, right? How is it possible to get the deformation value in millimeters when you have a resolution of in meters, right? Or even more than meters here. And is it possible to get the accurate deformation value using INSA without GPS validation? Now, in terms of the second question, how to say that? Actually, the second question in itself is missing some kind of logic there, because validation would just be to validate your results. You would get your accurate deformation value anyway without validation, right? You get your values, and they're hopefully independent of whatever you validate them with. So they always would, the answer would always be yes, right? I get the deformation value certainly without validation. But it brings me back to what we discussed also last time a bit. There is a certain wish always to validate everything, although we already know basically the quality that we can achieve with interferometry. So yes, there certainly we can do that without GPS, and that's also the goal, right, of remote sensing. We do not want to have a GPS station there. But let's talk a bit again how we can achieve that high precision.
Sorry, Professor, can I ask you a question?
Yes, ask them. All right. Or maybe write it in the chat then, it's also okay. So we are getting the measurement by the phase. So we are looking at the phase or the phase difference of a pixel. So we are not looking at anything on the amplitude. We are looking at the phase, and the phase difference, right, that we can measure, or the fractions of the phase distance that we can measure, considering the noise that we have, is a function of the wavelengths of the system and not of the resolution. So what we measure is fractions of the wavelengths. So if our wavelength is 3 centimeter, right, and we can measure a tenth of the wavelength, then we are about 3 millimeter, but we can measure actually even more than a tenth. So we can come down to measuring phase differences of millimeters with this technique. And the reason is that we are independent of the resolution in that sense, is that we're looking only at the phase differences, and they are as such not directly related to the pixel size. Okay, I said not directly because if we have a very large pixel size, we have more different objects in it that we probably need to consider, and there are different effects on that. But the measurement itself is a measurement only in that range direction. We're looking only at the differences in the phases, and they are dependent, and there's a function of the wavelengths and not a function of the pixel size. So that is the secret behind it, if you want. So, right, that we're looking only at that, and that's why we can say interferometry, the precision that we can achieve, does not depend on the pixel size, but only on the wavelengths. Clearly, when we go into practice, right, and when we are making applications, the pixel size, the size of the resolution cell also has a very big impact on the final product that we can achieve, right? That is if you want the resolution of your DEM that you can achieve, is also a function of or is mainly a function of the pixel size, right? So if you want the resolution of your DEM, the pixel size of the DEM that you achieve, that's going to be a function of the resolution of your images. However, the precision that you can measure each pixel then is a function of the wavelengths. I hope it made sense. Okay. Does the core registration accuracy depend on baselines of the two scenes? That's actually a good question, right? And the answer is yes and no. Okay, so actually the answer is yes. Let's be honest. The answer is yes. You can, if you have a large baseline difference, right? It's more difficult to co-register them. If you have a very flat scene, it doesn't really matter. They could have a rather large baseline. But if you have mountains in it, then the difference of the pixel position with respect to the topography and the topographic difference, they can get rather large. They can go over pixels. So if you have a very mountainous scene, you may need to include the DM in your co-registration. So yes, there is an effect. It's clear if you have a very large baseline. We discussed it, right, basically also with stereo radar parametry. If you have a very large baseline, the geometry gets more different. You have, in case of stereo radar parametry, it's going to be more difficult to find homologous points. Now for co-registration, you're going to do the same. So if they are rather large, it's also going to be more difficult. So yes, however, aside from like scenes with really like strong topography, really huge mountains and topographic differences in it, typically it is rather straightforward to co-register the scenes, and even with a rather large baseline difference, it's normally not a huge problem to actually co-register them in practice, right? It's still going to be possible even with larger baselines. So the co-registration accuracy depends on the baseline, right? Especially for very large baselines, but it is normally still not going to be a huge problem. The next question, I don't really know how to answer, right? How is it useful in marine or security? Well, if you have a sensor that can look day and night under all weather conditions, and that is especially very well able and basically designed to separate ships from water, it's a very good and useful sensor for marine or marine security related projects, right? So in that sense, right? Another question, actually a very good one. Can we use SAR interferometry to measure open water level change? So, for example, sea level change. And it's a good question. And the answer is no. Okay. So why is that? Well, if you have your typical calm water situation, say the signal will be reflected away, right? You get almost no signal back to the sensor, which means you also do not have anything where you can measure your interferometry mid, because you don't get enough information back. What you will get back is typically below the signal to noise, below the noise ratio, below the noise level. So typically the answer would be no. You can't really measure the height of water. What you could do is you could measure the height of land area very close to the water and see if your water is getting, if you in that way could measure water level. Now, we are not using SAR interferometry to measure open water level, but there is another type of radar, the radar altimetry. Those sensors, they actually measure the height of water, also sea level changes. There would be another radar sensor, radar altimetry sensor. They are actually nadir looking sensors, so that they're looking down so that you get the reflection back and then measure the distance to also measuring the runtime of the signal, not using SAR, also not using interferometry, so having much less spatial resolution, right? But you don't really need a very high spatial resolution to do that if you're interested in sea water, right? If you're interested in the sea, then even a very bad resolution is still good enough, right? However, again, talking too long, the answer is no. And the reason is you don't really get a signal back. Even if you would have, you could now come and say we have sea waves, okay, but the question would be, where exactly on the sea wave would your reflection come from? That's changing. It's a dynamic measurement. It's a dynamic, wave is dynamic, changing the height. And you are measuring in millimeters, so you would never know where you are on the wave by itself. So
đã comment như vậy.
the answer is no. Okay. Now, I also have to admit, I don't really understand that question, right? Do you think coherence can give good information about disturbance in the ground? We have to calculate other parameters to be sure of that deformation disturbance. So I'm not really sure what the author of the question was meaning with disturbance. Is it changes? Okay. But then on the second part, we come back to deformation. So let's assume it's changes. Okay. So yes, we have very good information about changes on the ground in the coherence. Our main problem is rather that the coherence is too sensitive for many change operations that we are interested in. But I will talk about coherence and also classification or change detection with coherence in a couple after the questions. It's basically directly coming. So I hope that helps you a bit. Then to also answer that question, but coherence itself is not a measurement for deformation. Okay, then we got questions on phase unwrapping. What do you mean by phase unwrapping? I use phase unwrapping for any application, and it's a standard threshold. And wait a bit. Okay, we'll come to that soon on the question of phase unwrapping. We will discuss that topic today, hopefully helping you to understand what phase unwrapping is. Maybe we can also talk a bit on some thresholds there. That's a good question, right? There was a question on how to interpret fringes, having some examples of those. And I like the question. I'm gonna prepare a bit of that, but I didn't do it for now. Okay, I will put it when we finish the interferometry part. I show you, I think, maybe some examples today, but I will put it more together. I think it's a very good question. And the best way to interpret fringes is actually, in my opinion, to not do that at all, but to move to techniques that do not force you to interpret any fringes, but instead come more directly to a measurement value. Okay, because interpretation of fringes is A, not easy, and B, often not what we really want. Typically, we want a measurement of them. Okay. Also, a question that is, a bit too far ahead. How can we combine velocity from line of sight direction with velocity determined using GNSS, or how can we combine GNSS,
video về với
SAR,
màn hình với tiêu đề
data?
đã không hay.
So the combination of the line of sight velocity with, for example, some measurements we got from GNSS. First of all, it's in the question, right? You have to make sure, understand that one is a line of sight measurement and the other one is not, right? So there's a different geometry involved. So you need to correct for the different geometry that you have. Then you have, on the one hand, with GNSS, typically you're going to have a point measurement, and from SAR you typically get more an area coverage, so that you need to combine them, right, in ways that you typically combine point measurements with area measurements. But beside from that, it's not a huge problem to do so. Both of them basically suffer from the same error sources to a large degree, especially in terms of atmospheric errors. They will be identical. So they are certainly combinable without too much effort in that sense, as long as you know classical GIS and geospatial information techniques of combining more of point measurements with area measurements. And yeah. Okay, kindly formulate research questions for research interested in SAR for ground deformation. I can't actually really do that for you. There are A, so many, and B, it would very much depend on what you are more interested in, right? Are you more interested in applications of it? Where could I apply such a technique, or more into further development, the measurement technique with SAR for ground deformation? That would be very different things to do. So what you need to do to get toward a current research question would be basically research the literature, look for current problems in it, and go from there, also including on what are your interests in it, because it's different from if you're interested in developing. If you're interested, for example, in developing methods for ground deformation to, for example, measure that better or solve some of the problems you're also going to talk about, that is quite different from saying, no, I'm looking for research. How can I use, like, what's another area where I can use that? So you're either going to be more specific, or you have to think of itself about it. Is SAR image used for forecasting of early hazard warning processes? And yes, sure. Right. That is for sure. That is, for example, right, early hazard warning, right, is, for example, also a good research question in that sense. Okay. So, yeah, sure. In different fields, certainly, for example, in terms of if we talk on motion, then it would be very much in terms of the landslides, right? Landslide motion would be a classical case, as we know that typically before we have a disastrous landslide motion, we see typically an increase in the speed of the precursors of the landslides. We see typically the speed along the landslide area, the surface motion speed, the velocity increasing before that. And if we can measure that with interferometry, but can we identify it before the hazard is happening? So that is still ongoing research or classical flood research, drought monitoring, and so on. So there are certain different approaches and different things in terms of forecasting. All right. Do we get the amplitude image and phase image both from the provider? Yes, let me show you what you get. That's what you get. You get if you order it, right, you get a complex SAR image where the amplitude of that complex number is on the left side and the phase of that complex number is on the right side. So yes, both is in the complex number that you get your data delivered in, and then depending on if you look at the amplitude or the phase of it. So yes, you get both as long as you order the SLC image, the single look complex image, where, well, it means you have a single look image, so only one look, and complex means it has a real and imaginary component. It's a complex number. So each pixel gonna be delivered to you as a complex number that you then can calculate the amplitude out by making the absolute of the complex number or the phase, by getting the argument of the complex number. So yes, if you order, the SLC image, if you order already geo-corrected amplitude image or something, then you will not have the phase information. Can you suggest me some algorithms used to reduce the noise in the SAR image? So as long as you refer to the speckle noise, that would be, there are various of speckle filters and speckle noise reduction algorithms available. Huge number of people worked on that, and normally your various software packages also have different sets of speckle filters available for you that can help you to reduce the speckle noise of your images. So the search term would be speckle filter for that. Okay. And interested in detect subsurface drainage in desert. What's your suggestion for me? Honestly, I can't give you any suggestion on that because I do not know much about that. So yeah, I'm sorry. That's really not my field. How do you correct for atmospheric effects in interferograms? That's a very good question. We come to that again. Somebody jumping ahead. Right. So first of all, you're gonna show that slide again. We know the atmospheric effects, how they affect our signal lengths, right? So if we basically what's happening is that our system, right, our signal is slowed down, which then we can also interpret as a change in the as a extension of the SAR path length, right? If our signal is slowing down, but we are still assuming speed of light, then actually, in terms of distance, our SAR path gets longer. And we know that very well because it's the same effect that we have on GNSS signals and GPS signals, right? And it's calculated in the same way. You have here the equation based on the temperature, the partial pressure of water vapor, the pressure of dry air, the amount of liquid droplets, and the electron density in the atmosphere. You can calculate the path delay. Typically, the problem is that you do not have these values in the resolution that you would need them. Okay, you get these values, you can download weather models, right? and then you can they include all these values. And however, in a very horrible, actually not that horrible, but in a resolution that is too bad, too coarse for you to really correct for them. But with these models available, we can correct for some of them, especially if you do not have a very dynamic weather situation, right? If you have a very dynamic and turbulent weather, you know, like rainstorm, right? It's very local, it's very locally very different. The water level, the water vapor content, the pressure and so on, changing very different and very dynamically, then these coarse resolution data will not catch that. Okay, but if you have a rather calm weather, where it's like a slow change in space and time using the right interpolation, you can actually correct now with the data a lot of the atmospheric effects. But still, typically it's not enough to really catch them. So we gonna discuss methods on how to do that within the data, using the data that you have. However, not today, probably next time or the time after that. Do we need to do any ground truthing? Well, that is a great philosophical question, right? Do we need to do that? And what does ground truthing even mean? Besides going into that discussion on ground truthing and the term, which just have been actually discussed by Ian Woodhouse in a new paper, do you need it? I cannot answer you that question because I do not know what you want to do, right? Are you working? What kind of project are you working on? Is it a project or do you develop a new method, right? So typically for many scientific projects where you would develop anything new, right? At some point you have to validate that. And that would require you to do something like a ground truthing. However, right, if we talk about using well-established techniques to measure something, you do not need to ground truth every step necessarily. Okay, very much depends on what you're doing and why you're doing it. Does the height always increase towards center point? All honesty, I don't understand the question. I have to say, I don't understand it at all. So does the height always increase towards center point? Well, with always, I would say probably no. Okay, can you explain the maximum displacement with the INSA, central one SAR, and if we can calculate the height of fringes, other things we can calculate. So, good. Yeah, so we're looking at the fringes. We are trying to, for example, calculate them, analyze them is one way of getting toward the deformation. Now, in terms of the maximal detectable displacement, the question is not so easy to answer. Now, in a very simple answer, the point would be the one you can measure, you have to stay below the phase ambiguity. So you have to stay below the 2 pi of your measurements, considering that it would be coming down in terms of displacement, something like it should come down to half of your wavelengths of your system, right? So if you have Sentinel-1, so from a pair of images, the maximum displacement would be 2.6 centimeter. However, it's not so easy, because if you have a deformation that is like smoothly increasing in space, right, then you can unwrap the different fringes. And again, I use the term unwrap without explaining it yet. Sorry about that. A few slides, okay? And then you can do more, right? Or if you have multiple baselines and you estimate them via some kind of linear estimation, you can, in theory, go above that maximum limit by solving the ambiguities with having more images with different baselines. So, right, the typical value that we can some Hoffer wavelengths, 2.5 centimeter between two images. So in terms of a Sentinel-1, that would be 2.5 centimeter in, what's that, 11 days. That would be the maximum displacement. That is more like a rule of thumb, okay? Because actually you, under the right circumstances, you can go higher. Okay. Oh my God. So many images, so many questions, so less time. I spent too much time on questions. Anyway, I like it. But let's move on. Can we have two sandwiches for InSAR to generate a better result? Yes, the answer is yes, and I will show you a couple of slides for that. Similar, that was InSAR for DEM, yes, and then for deformation, these here mentioned PS and S-bus InSAR products use even more images to get to better results, and we will come to that. So how we can generate them, I will explain to you in great detail after InSAR. Okay, then we go to more advanced methods. Can we use InSAR data for mineral deposit detection and species identification? No, right? Let's be short and clear. No, with InSAR we measure deformation and surface motion. If your deposit has a relation with surface motion, then probably yes. But I do not know if there's any such relation. So the short answer is rather no. Okay, great. That took a bit longer than I was thinking, but it doesn't matter. We are actually good in time with our course. So we are not behind in any way. And I really want to try to answer these questions. I can't answer every question. And now you saw some I pointed out and I say, I'm going to come to that. Okay. So sorry about that, but we really do. And if I did not answer the question because I didn't understand it, still the idea can be, maybe you can rephrase it, make it more clear to me. Also, I just before the course, I saw one email and I will take a look at that. Which maybe I can answer that better with more examples in it. Okay. All right. And last time we were talking about the coherence estimation. Right. We looked at how we estimate the coherence, calculating it. So basically, we include here the phase and phase differences. So we have a rather sensitive measurement in this coherence value here, and the coherence value here is limited between 0 and 1. Okay, so it's between 0 and 1 is the value that you get. Okay. And then we discussed that also from the equation, you can see this E, that's expected values. So we are combining a number of pixels. We're not only looking at one pixel. right? That would not work. Mathematically, you would get a result, but it would be not a correct result in any way. So we have we need to look at a number of independent samples, and that should be, you see, the higher our number of independent samples, the better is our estimation, right? But however, that is theoretically, what you need to know is also that you have, if you think about an image, right, and you create a large box with many independent samples in it, then if it's a very large window, now you may have different objects in the same window, which actually have a different coherence, and then you mix that, then you also do not get a good result at the end. So you should have a large number of independent samples of the same object, of a similar object. Okay, so there is certainly some kind of, you have to find the right middle way, because between a large number of independent samples and a suitable window size, right? And one way, actually, we're not going to talk about that now, but one way to do that better is to have some kind of adaptive filtering, to have a filter that, you know, it's not just a box, okay, but actually tries to follow the objects that you see in the image, so that you get a large number of independent samples of the same structure, right, or the same type of things. Okay, we'll come to that a bit. That is an important point, is the difference between distributed and point scatterers. We'll come to that a lot, that's why I repeat that slide. Just to come back to that point, we have the point scatterers. This is here shown as artificial targets, but they can also be natural or man-made objects like buildings. They're not really natural, but you know, they're also not artificial SAR targets. And they are defined as as point-like scatterers, and we also typically define them as having only one strong scatterer in a resolution cell. So as in contrast to distributed scatterer, where we have many scatterers, small targets in a resolution cell. If you imagine a tree, okay, the radar will be reflected from different parts of the tree, okay, from twigs here, leaves there, the stem, right? Maybe there's even some ground in that pixel, right? So different targets distributed over that pixel, they will reflect back together, and then you get a Speckle effect, because we have the Speckle effect defined as having more than one scatter in a resolution cell. And if that's the case, then you get your random speckle phase. Then you have to deal basically with Speckle effect again, and with the randomness or the quasi-randomness of that. So point scatterers, distributed scatterers will become very important separations later on, right? But they are very basic. It's because you have to treat them differently. Okay. Now we come to the coherence maps. So the coherence that we showed has two purposes, two important things you can do with them. One is what we typically use it for, is a quality measurement. So if you have good coherence, then we say, well, we have probably good phase stability, and the interferogram that we get has probably a good quality. Okay, so it's a quality tool, helps us to, to identify regions in the image where we maybe have good quality, can get a good phase result, and areas where we maybe don't. But it also has information on scene features, even things we can use to classify data. And that is much more seldom used in that way. So here's an example from Coherence Maps, also from Professor Rocca. Oh, this one is not the Vesuvius. This was the Etna, right? Another volcano in Italy. And we see on the coherence, if we have a white, that means we have a very good coherence, which would mean not much has changed, and black would be low coherence or no coherence, which would mean a lot has changed. Right, and so you can see areas where we have black low coherence. There would be areas where we find changes then on the volcano. You can, in that case, also follow lava flows and changes caused by outbreak here of Etna. Also, the coherence is very sensitive to vegetation, right? Because vegetation, in sense of radar, is something that changes. If you have a time difference between these two images, if you can imagine a tree, a tree moving in the wind, right? One time, you have stronger wind, or the wind direction changes, right? We are not getting exactly the same position of each of these small scattering objects of the tree each time, right? So if we have vegetation, typically means that we very quickly lose coherence, and on the other way around, looking at coherence, we can also identify, therefore, vegetation. You see that here, when we have low coherence, in that case, black, right, we would have more vegetation. When we have high coherence, we would have less vegetations. So it is also a tool for identifying, kind of identifying vegetations. So we are losing coherence over time, right? Because there's a time difference between the two images. We're losing dependent on the time difference. So in water, when we talk about water, right, we get, anyway, water is reflected away, so we can't really measure. But we also, even if we can, we get zero coherence after, in case of water, after milliseconds. Very, very quickly, changes very fast. Very dense vegetated areas, we also very quickly lose coherence. If you imagine again a tree in the wind, even if the few seconds, the positions are quite different. So if it's a larger tree, large forest, we may lose coherence very quickly. Now, agricultural fields, less vegetated fields, they lose coherence more slowly, maybe after a day, couple of days, maybe months, right? And other terrains like rocks or urban areas, they can stay with a very high coherence even over years. So by looking at that, how fast you're losing coherence, that can also be a tool to classify and identify targets or land use classes in an image. Okay, so that is also one thing we can use the temporal coherence for. Now, and then we can do such maps, okay? And the temporal coherence loss that we see is very, very strong. Okay, you see here after a couple of days, we already are you lose already a lot of coherence over that. And what does it mean if you're not interested in classification? Classification with coherence is still a very interesting field and also would be an interesting research question, as asked before. Now, we're not really going deep into that in this course, okay? It's a very interesting field. But today, in terms of interferometry, we are interested in that as a term of quality, okay, as a quality measurement. And we lose the coherence very, very fast, which means we lose the quality of our measurement very fast through temporal decorrelation. And temporal decorrelation means that things on the ground have changed between these two acquisitions, and so the signal is decorrelated. We losing coherence. We're not looking at the same targets in that sense anymore. So if we have complete decorrelation, our phase measurement is then becoming meaningless or even random. So it's basically the main limitation in repeat path interferometry. The temporal decorrelation is a very huge effect. Depending on the wavelengths, the longer the wavelengths, the less effect you have, and on the vegetation, the stronger your vegetation, the more strong the effect will be. Right, and here's a rather simple model of the temporal decorrelation, just assuming here such a twig on it, and you see with the motion around there, going up, down here. So if we have such a motion of, let's say, 0.5 centimeter or 5 millimeter, it's really not much, right? It's really not much in terms of motion of such a trick. If you imagine a tree, again, a motion of 5 millimeter, that's almost wind still, right? There's almost nothing moving. If you see that with such a motion in X band, you get already a very low coherence, less than 0.2. With C band, you're about 0.6 coherence. That is, usable, acceptable value, actually quite good value already. And with L band, you have almost full coherence. With a motion of 1 centimeter, you see for C band that would also not be good enough, but in L band you still can use also such a motion of 1 centimeter. Again, looking at that picture, and you imagine, go out, look at trees, 1 centimeter motion. That's also not much. Okay, just a little bit of wind going on, you have that immediately, right? So you can imagine in the shorter wavelengths like X band and C band, the effect of temporal decorrelation is very, very strong. While in longer wavelengths, the effect part is related to the wavelengths, right? There is also emotion there. Then if you have 1 centimeter in relation to the 20 centimeter wavelengths, right? Well, it's much more in relation to the 3 centimeter wavelengths, right? That's one part of it. There's another part of it which is not on that slide because it's just a simple model. If you have a very large wavelengths, you are also not really looking at these very small targets, at these very small twigs here. You will rather be reflected from the stem of the tree in that example, right? Which will also move less. Okay, so because you're going deeper in it and you get reflected from the larger twigs, the larger stem, they also by themselves move less, which also increase here your or decrease your temporal decorrelation for long wavelength data. So important to remember is if you have short wavelength data, X band, C band, the effect of temporal decorrelation will be very strong for basically wherever there is vegetation, especially large vegetation, high trees, dense vegetation. And when we have longer wavelengths like L band or P band, that effect will be smaller. Then we have, beside temporal decorrelation, we also have different ways of coherence loss. One would be the geometric coherence loss. So we are losing coherence based on the spatial difference between these two. So if they are rather far, if you have a rather large baseline between the satellites, a rather large spatial baseline, perpendicular baseline, we are looking at them then a little bit differently. And especially when we have such distributed scatterers, so when we have many scatterers in one resolution cell, then we are looking at them from a little bit different angle. We may see them, we may see different aspects of them. That's one part of it. The other part is they are now so like with respect to the pixel, they are now at a little bit different positions within the pixel, within the resolution cell, and that difference gets larger if I have a larger difference between the angles, right? And then the Speckle effect comes that now I get a different result. They interact differently with them. So we can then have what we call the geometric coherence loss, and that gets larger. The larger is our baseline between the sensors. The one part of also of geometric coherence loss would be for shortening the correlation. So when we have, for example, that mountain, the area, the side, the mountain side looking toward the sensor is going to be shortened in the image in this foreshortening effect, which also leads to a decorrelation, so-called foreshortening decorrelation, which is also a form of geometric decorrelation that is related here to the geometry of the topography of the mountain. So if you have such a steep mountain, we may find that we see decorrelation in that mountainside area, especially on the steep sides of them. Right, there's another example here where we see the rather low coherence on the to do the foreshortening, like this one. So the line of sight is in this direction. So in this area, for example, has very low coherence due to the foreshortening effect of it. So again, there's also one form of geometric decorrelation where we lose coherence, in this case to the image geometry and the satellite geometry. Another form of coherence loss is the volume coherence loss. So if you have a volumetric scatterer, so if we have a scattering when our signal enters a volume, for example, a forest canopy, and gets reflected many times inside the volume, this also leads to a coherence loss. Again, the amount of coherence loss in this case is also related to the baseline difference between these sensors. So you see if you have a very short baseline, we have not so much coherence loss compared to a very larger baseline, where we lose coherence here very fast in a volume. So if we have a volume scattering, that also means that we see relatively fast coherence loss. Now, volume scattering, I used the example of the forest, right? When we have the forest, we will also have, if we have a time difference between them, we will also have a temporal decorrelation, which is typically much larger than the volume coherence loss. So in that case, we will lose coherence even faster than here. But clearly, both of them will in reality come together, and you will lose, again, coherence in such forests or under such circumstances through to temporal decorrelation and through to volume coherence loss. And so you're going to lose a lot of coherence in forests. Another effect is the atmosphere, clearly. So our signal is traveling through the atmosphere and it is delayed through the ionosphere and the troposphere, not traveling the speed of light anymore. Now, the main problem here in that case is not the delay itself, it is the spatio-temporal difference of the delay. So it's going to be different, the delay is different depending on the weather situation, and that is a spatio-temporal difference. So the weather is different in space and in time. So you have different delays through the atmosphere, which can be easily in the range of centimeters. Actually, a couple of decimeters is typically the amount of dynamic delay, while we measuring millimeters. So the delay of the atmosphere can be very severe. And what we are especially worried about is the spatial and temporal delay difference of it. I showed this slide before, just a point here. So we know the values, we know what is causing the extension of the SAR path. We know that from basically from GNSS, from all the research going on in the field of GNSS. The delay is the same. Okay. So we can, if we would have all the values, we could calculate it. Again, the problem is that we do not have them in the resolution, in the spatial temporal resolution that we would need them to. Right. The ionosphere here plays also a big role in it, the total electron content. Again, this is also values that you can get. This is available from GPS centers, and this is an important part of GNSS research. So you can get it there, you can correct for that. This one, in contrast to the ionospheric phase delay, is dependent on the frequency of your system. So there is in shorter wavelength, CX band, there is not much influence on that. That is mostly then dominated by the atmosphere, the tropospheric phase delay. But for longer wavelengths, the ionospheric wave delay, path delay, is much more severe and can dominate the overall effect. We can, as written here, we can compensate by multi-frequency processing, but at this moment, that's not going to be possible for you with SAR, because typically you only have a one frequency available for you. Okay, now this atmospheric delay, especially water vapor, would be playing typically a major role in it. They cause delay, which then distorts our phases, because delay is different in space and time between these two images. So you see over an image, we have different phase delays. This is array between -8 and 8 millimeter, so more than 1.5 centimeter phase delay. So that, and you see on the right side on the weather image, that is a rather calm weather situation, right? That is not a huge rainstorm or something. It's very calm weather that we have here. But the slant delay is already several millimeters, almost centimeter. I mean, almost 2 centimeter, which is quite strong. And if you want to measure here in millimeters, that can be already too much. Right. So the troposphere, the delay is frequency independent. So you could get the same range error dependent of your band. You could also then in that phase, you could not compensate it by multi-frequency processing. And it can be large errors, but these errors, they are spatially dependent. Okay, by that we mean from, if you think about the weather from one pixel to the next pixel, right, the weather is not going to change so much. Similar, the phase delay is not change much from one pixel to the neighbor pixel. It's going to change slowly over the image. So it is spatially related. It's not just some noise over, it is a spatially related noise, which gives us the opportunity to correct for it, okay, within the data, because we know that this kind of error is spatially related. So that's very important information. And some other sources of coherence loss would be, not optimal software, not optimal processing of it. So that can, there can also be a quite big difference in coherence depending on the software you're using or the non-optimized implementation of it. So that can also, and you see there can be a rather large difference, which clearly should be avoided though. All right, so when we're looking at the summary of the contributions to the coherence, we have the temporal decorrelation, which just says we cannot avoid, we can avoid it in a way if we are able to reduce the time difference between both images close to 0, then we also remove the temporal decorrelation. The geometric decorrelation can be improved when we have a very small spatial baseline, right? When we have a small spatial baseline, then we can improve that. Volumetric decorrelation cannot really be avoided. However, the processing decorrelation from processing errors, from software errors, they clearly should be avoided as much as possible. And that also summarizes you problems with the quality of your SAR. What are possible error sources for your interferometric measurement, because the coherence is related to the error. So if you have a strong temporal decorrelation, you will not get a very good result, okay, at the end, similar for all the others. So it's not just a summary of the coherence as such, but also of the different error sources that can be there. Now, if we still talk on elevation, on height measurement, we can use the coherence and give there a relation between the coherence we can achieve and the expected quality or error at the DEM that we can calculate. So by putting it here in the equations, we can, for example, if we have a very good coherence of 0.9, we may reach elevation, deviation, error, if you want, from the elevation estimation of something like 80 centimeter. But if we have a coherence of just 0.5, then we already have much higher error of probably about 3 meter of it. So we want to have, for sure, very, very good coherence so that we do not have much noise in it, so that we get good and meaningful results to create our DEM or also our motion, if we talk about that. So the coherence is very, very important. Right, again, looking at the here two interferograms. On the left side is a single look interferogram, which you see is rather noisy. And on the right side, you see the multi-looking interferogram with 5 looks, multi-look. You see we already removed quite a lot of the noise. And we talked about multi-looking with speckling, right? I mentioned the speckling effect is very strong, especially also for the phase. So it is important to multi-look to get an average over 7 pixels when you are processing distributed scatterers, which is the normal case, right? Normally, most of the pixels we are looking at are distributed, have distributed scattering in it. So multi-looking the data is very important, and we can see the importance of it also here, not really in that example, but let me explain you what I mean by that. So the importance of multi-looking, we can see in how many SAR satellites are actually already designed. Here in the example of the ERS, the resolution of the ERS sensor, also the resolution of the Sentinel, for example, is not the same in azimuth and in range. They have different resolution in azimuth and in range, and typically in case of ERS and in case of Sentinel, they are one side, one direction has 5 times less resolution or 4 times less resolution, right? And they are designed in that way so to directly give you the option to multi-look them this 5 times. That's why we have here 5-look interferogram, just to get back to square pixels, right? And so then you have the same pixel size in azimuth and in range. So you can see that this multi-looking is basically in the system already by design, right? The system has been designed with the mind that people most probably gonna want to multi-look those things, let's say at least 5 times or 4 times. So there you can see that it's already in the satellite design. People say, they're gonna multi-look anyway, okay? So we give them different resolution, azimuth and range, and then they can directly multi-look. Not all sensors are doing that, but it's quite common. And so multi-looking of your data is important, and I would say it's a standard procedure for it, and especially for phase. If you have distributed scatterings, you will not get, typically not get meaningful and good results without multi-looking. There are some exemptions to that, and we will come to that. But as long as you have distributed scattering, multi-looking is the way to go. Right? You see here the phase standard deviation given in degrees. Often we give the phase in radians from -pi to pi, but we can also express them in degrees. Right? And you see, if we have no multi-looking, we have rather high phase errors, even in rather good coherence, just in very, very, very good coherence at the end of that, we come to lower phase errors, lower standard deviation of the phase. But it's already with 2 looks, you see, it's already getting much better. And with 5 looks, already much improvement in terms of phase error here. So it's just a few looks, it's just reducing the resolution by 5 looks or 10 looks. You already get very good, much better, phase error behavior. The reason, again, it is the Speckle effect. The Speckle effect is very strong on the phase to reduce speckling and errors like speckling. What we need to do is we need to create statistics and then, for example, the average of the pixels in a window would be the easiest form of statistics. And similar here, another showing you with less clarity, even more. The similar, basically, just with even more looks. So it's up to 128 looks. You can see the effect of having a lot of looks here on it. Okay, now, and we have our interferogram. We may also want to filter that. And yeah, it's not a nice slide, actually. It did not come out as good as I was hoping, because it's not in the middle. So see, on the top of the slide, above the line I'm drawing, is the filtered interferogram. Okay, and below is the unfiltered one. Okay, so here somewhere is the line between filtered and unfiltered. Should be more in the middle. It's a bit shifted down, but you see a huge difference in it, and that is because people have developed special filters, especially for phase. So there are filters available. The standard would be the so-called Goldstein filter, which are optimized for phases, and they provide you, relatively good filtering results. So it is also advisable for many applications to actually use them to improve your phase quality, not only by multi-looking, but also by filtering, by interferogram filtering. Okay, you see, with the phase being ambiguous, good fringe quality is very, very important, right? Because if you want to unwrap them, if you want to count along these fringes, on the left side, you can imagine we would be able to do that. But if it's very noisy, like on the right side, if it's very bad fringe quality, we will have a very hard time to process the data, to unwrap the data, to, if you want, count these fringes along the line. The spatially correlated noise, that is typically the atmosphere. It's not the only spatially correlated noise, but typically that's the atmosphere as it is slowly changing. Also the path delay is slowly changing over your image. We call that spatially correlated. And we're going to use that property of that noise later on to correct for it. So our knowledge that the atmospheric noise is spatially correlated, slowly changing in space, we can later use to separate that from other noise sources. So the atmosphere here, that's another example of the atmosphere. And we call that, right, important word here is we call that the atmospheric phase screen, right? APS, the atmospheric phase screen, that what we then call these, we want the phase noise, the phase error caused by the atmosphere. That is often called here the atmospheric phase screen. All right, that's where I wanted to come today, to the process of phase unwrapping. Now, phase unwrapping is a not an easy task, right? So let me walk you through it, that you at least understand why it's not easy and why there are problems with phase unwrapping. So we have the interferometric phase, right? But it's not giving us like in absolute values, it's given us in these wrap values. So we have it's wrapped between minus pi and pi. We can express that with the W, the wrapping operator. Okay. So now the phase unwrapping problem is that we have the wrapped phase. That's what we have. We know the phase between minus pi and pi, but we want the true absolute phase, the unwrapped phase, right? So you want to move from this one, right, to this one inside the wrapping operator. You want to unwrap it. You want to get rid of that wrapping operator. However, that's an ambiguous process, okay, because you have that absolute value that is wrapped only between minus pi and pi, and we do not know in which way it is wrapped and what was the absolute value before. So there are many possible solutions, which makes it an ambiguous problem. There's more than one solution. So we need some additional constraints to solve that problem. And then we are going to find the most likely phase. And that's a term which we do not like, right? Because it means, well, it's probably the right phase, but we are not sure. It's just the most likely one. We do not know it. It's just the most likely solution, not for sure the correct solution. So it's something that we do not really like, right? Also, we need to add some additional constraints. For example, typically we add some smoothness constraint. That means we would say, well, you know, let's say we want to unwrap the faces a lot up, going up this mountain that you saw, okay? And I told you we count the faces, right? And then we can go up. This has a constraint in it. This already has the smoothness constraint in it. We expect the mountain side to go up smoothly, right? And then we can count them. This is an additional constraint, right? Because it has to be like a smooth mountain that normally goes up, which is certainly true for most topographic features, but not for all. It's also, for example, not true for buildings, right? Buildings do not go smooth. Buildings go no building with suddenly very high height, right? Building end back to the road. That's not smooth, right? Now, you could add another constraint, right? You could add a kind of building constraint and still be able to unwrap it, but it would be another method, right? Typically, we have some smoothness constraint that we say, well, it has to change smoothly over the image. All right, so what we're going to do in unwrapping is, here's an example of 1D phase unwrapping, so just one dimension, right? If you look below at the blue line, right, that would be what we have. We have the phase between minus pi and 2 pi, right? That's what we have. Now, it is very likely, if we look at it, that actually instead of the phase here crashing down, it's actually more likely that it's here just like a smooth smoothly moving over the pi limit, right, and just continue going up the phase in that sense, right? And here also it's more likely that the phase is just smoothly continue to go up and not just suddenly break down, right? So that would be here, that solution that we see here would be the most likely solution, that we have a smooth phase change and not sudden jumps in the phase, right? Again, what we see in the data would be, right, that part below, right? I mean, they are all the same here. That's what we actually see. And in phase unwrapping, we try to combine them so that we go beyond just from minus pi to from minus pi, to 3 pi, 5 pi, 7 pi, and so on, to unwrap here along and get some absolute phase value. Now, the 1D phase unwrapping problem, if we just have one dimension, right, is actually very ambiguous and often not really solvable. So if you see here the original phase value on top, right, then if we wrap those phases here, and we try to unwrap them, you see we may end up here with an, as you hear, we have the unwrapped phase values that we have here, but they differ from our original phase values. So we have here an unwrapping error. Here it's caused here by that one. At the end, we did not unwrap this one correctly. So we end up with an unwrapping error. And so our estimation of the unwrapped phase is not the same as the original phase value. There is some similarities to it, but it's not estimating that one correctly. For Andy, phase unwrapping is very, very difficult, because if you have, one problem in it, you have at the end no way to solve it, because it's ambiguous. You don't know, did I do it correctly or not, and you can't really fix it. Now, if we have a 2D phase unwrapping, it's actually easier, because if we have with one pass, we can follow the phases along different paths. And we can go like this around a pixel, or this to come back to the same pixel. And if one path has an error in it, we can fix it by different passes of it. So again, taking a look at the phases here with a smooth phase change of something like a smooth mountainside, we would go, we say we can follow them, and to do that we would look at the real and imaginary paths. And one way to do is to say they should never cross, right? And then we can follow them up these mountainsides. However, in reality, if you have some noise, such kind of noise may cause you here, for example, to cross them. The real and the imaginary parts, this kind of noise may, if you look at the fringes and just imagine you would try to follow them, if you have some noise, you may find out that, oh, here I can't be sure, right? Where is it exactly the phase jump? Where's the phase going on? So then you end up with probably errors in the phase unwrapping. Now, what you can do a bit is that we can look always around, for example, in circuits around the pixels, because we have 2 dimensions, and we can try to see if we add the phases up and go around, we should end up, if we add them up, we should end up at the same values again, right? Otherwise, we have, like here, we have some problem. Then we can say this is a residual of the phase unwrapping, and we can then try to fix that for example, by adding, by creating such a deep hole and trying at the end to fix these residuals, right? And we can do that, right? If we have only one dimension, we can't do that. But if we have two dimensions, we can go around and try different paths and different directions to connect them. Now, one more word to the most likely solution. On the left side, that is the DM on the left side, right? It would be smooth and therefore the more likely solution than the right side. However, that is all right and true, but it might not always be the correct solution. Although it's very unlikely that your mountain has such jumps and going down, you can imagine, for example, volcanoes where you find such crater or such structures that are probably not likely and certainly not smooth in that sense. So, although we have good phase unwrapping solutions, they are ambiguous and they have constraints like wanting a smoothness, which is not always given, right? It's not always representing the reality of it. So working on something with having a most likely solution is already like, I don't like that. Right? That seems to be, there might be errors happening, and they are. Besides that, now having a look at, if you have the software in front of you, what you're gonna do, okay? So most of you will not gonna program your own phase unwrapping solution, okay? You want to use that, right? So be aware, phase unwrapping is ambiguous, there are errors likely to happen, and it may even fail, right, for you. Now, beside these warnings, what are we going to do when we do it now? Step one is basically, before we start phase unwrapping, what we normally want to do is we want to mask out low coherence areas. So we take a look at the coherence image that we created, and we say, well, areas where we have very low coherence,
but nothing out and out. But
they will not give us good results anyway, right? So we better mask them out because we do not want to spend lots of time unwrapping noise, okay? Because it's useless, and it's going to cost you a lot of time because the unwrapping algorithm is going to try to find a solution to unwrap and follow the phase in the noise, which will take a lot of time and is futile anyway, right? Because it's noise. So step A is typically to mask out low coherence areas. Now, we had the question on that before, right? What is a good threshold for that? There is not one threshold value that I could tell you, because otherwise it would be fixed in all softwares, right? But certainly, let's say, normally less than 0.3 of coherence or less than 0.2 coherence is often, not going to give you good results anymore. So you're going to have to look at your data, how much of the area that would affect with different masks, and then make a decision. But there is certainly a limit below that. You will not expect any good results typically. So after masking the low coherence area, you can start the phase unwrapping process. And there are, let's see, depending on the software that you're using, there are, you may have to choose between different algorithms and approaches. And you see, I have here an example with two. They are similar but not identical, right? So we're gonna have especially larger difference between the two. What this color we don't really see so nice. Here. No, no. Maybe this. Now we see it even less. White, maybe. Here. No, that's also not white. Okay. Right, this area, now I found it. Okay. Right, it's quite different from that area here. Right, and that's just two different approaches. Now, the question that comes then, right, which one is better? I get that question. And again, if there would be one algorithm that would always be better, the software would not give you 2 or 3 or 4 to choose from, right? They are different. And there may be better suited, one might be more better suited for some applications or terrain or objects than others. Right? So, for example, if you look on the right side, there is less phase differences here. So maybe in that example, that one's going to give you less noise there, or more smooth DM at the end. While on the left side, that one may give you, maybe exactly that topographical difference in that area that you're looking at. If you're very much interested in the small changes there, that's maybe, actually what you want to see. So it very much depends on, what you want, and also on the data you have, on the topography that's there. There is no silver bullet for all of them. And so unfortunately, there is not a clear answer of which one is the best. There's just not. Okay, and then from the phase unwrapping, after phase unwrapping, which again I cannot put that enough, is also a process that can actually and sometimes does just fail, that you do not get good results, that you cannot phase unwrap, you only get a result from half of the image, it's crashing, it's not reliable, your result. There's something that can cause lots of problems. That's because it's an ambiguous process that has certain constraints that you may not be able to fulfill. Like a smoothness constraint that's just not always given. Now, after the phase unwrapping, right, we then can get such an interferometric height map where we can then say, well, it's so many meters per cycle. We can then transform that to ground range. We actually don't really need to do that. Typically, would instead of ground range, let's say we transform it to the world coordinate system, right? We can that now. We have the height, we know the coordinates. We transform it from radar coordinate systems to world coordinate systems, and then you can create your digital surface model, which then would look something like that. Again, it is not uncommon here to have in such a model here rather large void areas where you, for example, here, this area we masked out because the low coherence. You see, we did maybe here not get good results on the mountaintop. Maybe there was also for shortening the correlation or other effects, maybe some shadow effects behind the mountaintop, where we just don't have data. So you will end up with something like that. It's quite common that you have voids in the results that you can then think about closing by using more data, different data, merging different DSMs. There are then solutions for that. What I want to say, that is common that you have voids in the data, right? That is what you're going to have to expect if you create such a DM or DSM in that case. All right, okay. That's it for today. Thank you for listening. And let me ask Sishan, do we have some questions so far?
Yeah, Professor, we have some questions. So I
then
will share.
I stopped sharing. I will try to answer some. And maybe again, we have to do more next time. Let's see.
Yeah, okay. Oh, no, a little bit more. Okay, can you see, Professor, screen?
I see it. Yeah, okay.
Okay.
Okay. Okay, all right. So, all right, I see. It just let me check. Okay. All right. Does the resolution get modified in interferometric DM processes? No, I'm not so sure what you mean by modified, but what we typically do when we process the DM is we want to use multi-looking, okay? So we are going to reduce the resolution by multi-looking the data. And so it's very common that you have then that the resolution of your final DM will be lower than the resolution of the SAR data that goes into it. Right? So we are typically downsampling, multi-looking the data to get to just deal with the noise. Okay. Is it possible to create DSM from TerraSAR and Snap? I don't know. I guess so. Actually, I'm not really an expert with Snap software. And how can I choose orbit there for TerraSAR? I do not know how to do that in Snap. However, the orbit of the TerraSAR data will be in the metadata from the TerraSAR image. So you will not need to download any orbit for that. That should be already there. Do SAR signals reflect from water surfaces? And the answer is yes, but they are going to reflect away from your signal. So you have a side-looking system. This is my water. Right? It hits the water surface. It's going to reflect, but it's going to reflect away, and you get almost no signal back, which is the reason why SAR images for the water is in most cases is black, right? Because we do not get any signal back. Difference would be when there's strong waves or something like that. And the last question I'm going to answer today is, what is the difference between INSAR and de-INSAR? We're going to talk about that, next time. We're going to reach that next time, for sure. INSAR means SAR interferometry, and de-INSAR is the differential SAR interferometry. So INSAR, basically we can say we use, INSAR is also the larger word, so de-INSAR would be a part of INSAR. But to make it simple, we use INSAR for create DEM and de-INSAR for look at motion. Okay, so de-INSAR for motion, INSAR for DEM. Okay, right. So I will answer the other questions later on. Okay. Give me some time to prepare them better. And
Hello, Professor.
Yes.
Can you please arrange one demonstration for the insert? We understand the theory, what you taught, but if it will be more helpful for a demonstration, those steps, right?
Right. That's not going to be part of that course. Okay. We are thinking about doing a practical course later on, but it's not going to be part of that course. Okay.
Hello, Professor. Could and can I get your video recording also? Can we get your video file recording also?
Yes, we're gonna have to discuss that with the Bell and Road Center. Okay. I think we are working on that. I'm not sure at this moment in what way you can get the video recording.
Yes, because I missed last class. That's why. Thank you,
I
sir.
know, and we are very interested in providing the video recordings. We are just currently discussing in what way, where we can, like where we put them on the internet and in which way you can access them. This is not yet finally decided.
Yeah, thank you so much, Professor.
Okay, we know that. We also, I'm interested to make them available to you. Okay.
Thank you very much.
All right. Thank you for joining. If you have questions, also write them in the chat and we will try to answer all of them as good as I can. Sometimes I don't know the answer also, but I will try as good as I can. Okay. Have a good night, good day, wherever you are. And
Good night,
bye.
Professor.
Good night.
Thank you, sir.
Thank you. Bye
Good
bye.
night, sir. Thank you so much.
Good night, sir.
Shishi Laushi.
See you last course.
Okay, bye-bye for
Bye.
Thank you very much.
Okay, bye guys, everyone.
Hello, hello, Prosper Vasha.
Yeah, what you want to say?
Sir, you sent a PDF, sir, but that is password protected.
Oh, okay. I sent a password to you in the meeting. Please just have a look on that. BRGTC. Okay, this is the password I just sent. Please check. Any other question from any one of you?
See you.
Okay, thank you.
Okay, bye. Have a nice day. Okay, let's finish it.
Record.